Hi, everybody. We had a problem in the number theory text in the beginning of the first chapter. We want to prove that if we have n to the third power minus n, where n is any positive integer, we want to prove that this is always divisible by 6. So what we did is we factored out the n, and we have n times n squared minus 1. Then we factored the n squared minus 1's difference of two squares. Those n plus 1, n minus 1. And if you notice, there's 3 consecutive numbers here. Well, the argument we made is that if there are 3 consecutive numbers, at least one of them has to be a multiple of 3. Because if you take 3 numbers in a row, at least one of them has to be a multiple of 3. Furthermore, if there's 3 consecutive numbers, at least one of them has to be a multiple of 2. It's possible that 2 of them are multiples of 2, but for sure, at least one is going to be a multiple of 2. Well, if we know for a fact that we have a multiple of 2 in this product, and we also have a multiple of 3 in this same product, well, that means that the product is divisible by 6 because 2 times 3 equals 6. I'm pretty sure I learned that in elementary school. Let's take a look at we tested this out. Let's take a look at the test of this. Well, in column A, I just have the positive integers. In column B, I have that's a1 to the third minus a1. So if this is my n, that's n to the third minus n. This is a2 to the third minus a2, which is 2 to the third minus 2, and so on and so forth. That's column B. And in column C, column D, I can't read my columns anymore. Whatever that column, why does it say column D? It doesn't make sense. Oh yeah, I put my glasses on. It is column D. Because I put column B is just to create a little space. So we have the number in column C divided by 6. And I just wanted to see if there would be any decimals. Because if the numbers in column C are divisible by 6, then there'll be no remainders here. If the numbers are not divisible by 6, I would get like 165.7 or whatever, or point whatever, I don't know. Or probably 0.33333 or something like that. Yeah, you get the point. Anyway, that, my friend, is the story. So that is that really now this is not a proof what I'm showing you on the spreadsheet, but we're just kind of testing out the theory. So we see that all these numbers in column C are divisible by 6, as shown. When I divide them by 6, I have no remainders. Again, not a proof, but we did the proof already. We already did the proof. Now we're just kind of like testing it out in reality. Usually works the other way around. Usually we test it, we see it in reality. I shouldn't say usual. Usual is a subjective word, but often we see this pattern, and then we notice it on a spreadsheet, or we notice it wherever, and then we go do the mathematical proof to find it. But sometimes it works both ways. Either way, that was one problem. Now let's look at the next problem. The next problem, actually we did this problem first, but whatever, is to derive a formula for the sum of the squares of the odd numbers. So we have 1 squared plus 3 squared plus 5 squared. We'll look up here: 1 squared, 3 squared, 5 squared, dot dot dot, plus 2n minus 1 squared. So because if I go through now, what's 2n minus 1? N could be any positive integer. So 2 times 1 minus 1 is 1. 2 times 2 minus 1 is 3. 2 times 3 minus 1 is 5. That's why it skips. So when I look at 2n minus 1s, even though n is running through all the positive integers, but 2n minus 1 only winds up being the odd integers. By the way, if I did 2n straight, that would be the even integers. So we want to derive a formula, and we want to use the fact that we already had a formula for the sum of all the squares, not just the odd squares. So let's look at a bigger. So this series here is part of a larger series of 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus dot 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 plus 2n minus 1 squared. Let's not forget that, plus 2n squared. Okay, so here we have all the numbers, all the positive integers from 1 all the way up to 2n, and that includes 1 squared, 3 squared, 5 squared, 2n minus 1 squared. So everything is in there. Now I'm going to take this and break it up into two. I'm going to I'm going to take it and break it up into two series, which I could definitely do because it's a finite series. You know, sometimes when they're infinite series, you got to be careful how you mess with them. But a finite series, for sure, I could do it. As 1 squared plus 3 squared plus 5 squared. So here's all the odds: 2 squared, 4 squared, 6 squared. Here's all the evens. Now, for the even part, I can. Oh, by the way, the odd part, I'm just gonna call it Q, just because I want something. It's just less to write. And the even part, I'm going to factor out a 2 squared. And I have 2 squared times 1 squared plus 2 squared plus 3 squared, that plus n squared. Because when I take a 2 squared out of 2n squared, I wind up getting 2 squared and n squared. Okay, now we already had shown previously through induction that this sum from 1 squared through n squared, that's all the positive integers, is n times n plus 1 times 2n plus 1 over 6. And 2 squared, of course, is 4. So the excuse me, so this here, which is Q, plus this here, which is really winds up being 4 and n plus 1, 2n plus 1 over 6, is equal to this second row right here: 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, up to 2n squared. And I'm going to figure out this second row by taking the formula for squares, because this is all this is all the integers, but I'm going to substitute 2n for n into the formula. So let's just do that right now, and let's see what we got. So now I want to mention that. Wait, am I recording? I can't tell. Now I am going to write the explicit formula for this, but before I do that, I want to solve for Q. So Q, if I subtract this, bring it over to the other side, Q is going to equal this whole thing with up to 2n minus this fraction here. And that comes out to be, now here I have 2n plus 1, 2 times 2n plus 1, which is the formula for squares, just plugging in 2n in place of n, over 6, minus 4n, n plus 1, 2n plus 1, which is what I derived in the previous page. Now, I'm going to do some combining. I'm going to factor out a 2n and a 2n plus 1 from both of these guys on top. So I have 2n times 2n plus 1, and I'm left with 4n plus 1, which you see that from right here, minus 2 times n plus 1, because that 4, I took a 2 out of it, so there's only 2 left, and so to speak, and there's an n plus 1. And now when I combine this, 4n plus 1 minus 2 times n plus 1 is 2n minus 1. So I've shown that Q, which is what I solved for, is equal to n times 2n plus 1 times 2n minus 1 over 3. And we've derived a formula now for the sum of the odd squares. Let's test out that formula in our spreadsheet just to see how it goes. So let me explain how I did this. So here we have, again, column A is all the positive integers. Column F, so that if you look here up on top, that's 2 times A1 is that number right there, minus 1 squared. And here we have 2 times A2 minus 1 squared. Now A2 minus 1, that's 2 times 2 minus 1, which is 3. So this is 3 squared. This is 2 times 3 minus 1, which is 5, and then squared, which is why I get 25. So here I have all of the odd squares: 1, 9, 25, 49, 81, 121, and so on and so forth. See how cool that is? Now, in this column, all I did is, well, I started with 1. All I did here is that I'm adding the 9 to that 1. So this number here is really 1 squared plus 3 squared. This number here adds the 35, adds the 25 to the 10, because it's, you see what we're doing here, and you can see that right here in this thingy thing. It's adding F. I really gotta put my glasses on so I can see. It's adding F3 to G2. But that means this is really 1 plus 9 plus 25, which is 1 squared plus 3 squared plus 5 squared. So this column G is really just the regular sum of the odd squares. This column, so that's n, because A3 is n. That's 2 times n plus 1 times 2 times n minus 1, and then divided all by 3. So I have n times 2n plus 1 times 2n minus 1, all divided by 3, which is exactly what I got down here. So what I have here on paper with my handwriting, that is an actual proof. What I have here on the spreadsheet is not an actual proof. It is a sort of a demonstration, because you could show that in theory, you could show that something works for a million. You could run this for a million cases and it seems to work. That's not a proof. And there are times when formulas do work for a lot of cases, but they turn out not to be true, in general. It happens. So let's just yay, this is what we did yay, this is what we did. I'm out.